Today I will talk about the color perception, color psychophysics, and how it could be a model for the relationship between geometry and relativistic quantum mechanics. So before starting, I would like to thank the organizer for invited me, and also Yasmin to present to me, Thomas and Roman, and this is the key of my presence there for this meeting. So what I would like to show you today is try to show you how color psychophysics could be a good model for fundamental physics, and in which case color vision could be a model for physics, and in which case it cannot. So before that, for sure, I would like to introduce some elements in psychophysics and in color vision, because probably not all the people are familiar with that. So psychophysics is a long study, is an ancient study, and the goal of psychophysics is to relate the physics of the simulation with the perception by a human observer. And in psychophysics, we believe there is a function. There is a function that relies the physics and the perception, and probably there is also an inverse function which relies the brain to the action on the world, so the motor control of the body and so on. And what we can ask in psychophysics is this function simple? So does it has a simple mathematical properties? So like, is it bijective? Is it universal? So does anybody share the same function? And how we can evaluate this function between the physics and the perception. And finally, how this function evaluates in time, in the lifespan of an individual. So a way to introduce color vision is the following, is to compare what could do a system of camera compared to the natural eyes and the natural vision. So this is the kind of paradigm I use in my study, and it's very interesting because you can compare what the eyes do with the camera, and you can simulate in the camera what the eyes do, and see what is important for vision and what is not. And also you can do modeling of the camera that help to understand how the vision works. So the framework is the following. So we consider the physics of the light. So the physics of the light could be classical physics or quantum physics. And then there is the acquisition of the scene by either the camera or either the eyes. And the acquisition goes through two different processes. One is the mosaic sampling. So the eyes on the camera have a single color sampling at each position of the image. And those sampling components are three, there's three different components. So for the camera is RGB, and for the eyes is L, M, and S for long, middle, and short wavelength. And then those acquired image have been processed. So by the camera, it is processed as a computer. So a computer has to process the image to make it available for displaying or recording on a computer. And we can also consider that the visual system has to do some processing, because the eyes acquire only one color per position, and there is a process in regulation. There is a lot of process of regulation inside the eyes. So those two processing are almost nonlinear. So this is the framework I use in my work to guess what could be the color vision, and how we can use this color vision model to improve algorithmic in the camera. So start by F is bijective or not. So F is not bijective. Why? Because you could have two spectra like those two spectra, which are very different. So it's different energy spectrum of the light, but they can give the same kind of hue, the same kind of percept of hue. So there is more, so the space of spectra are bigger than the space of perception in some sense. So there is a reduction of dimension in between the spectra and the appearance of a color. And also we can say that if you have an object like this and it is illuminated by a particular illuminant, and if you change the illuminant, actually you change in the picture there, you see that there is two different color, okay? But if you were on the room with the object, and because your system will adapt to the illuminant, you finally will see those two images the same. So actually, with adaptation, your brain will encode the color of this object the same, which is white. So just to say that the color vision mechanism are almost complex and difficult to model mathematically. So I would like you to do your own experiment, and this experiment is about your color adaptation, and you can test it by on yourself. So what I ask you is to fix that cross, the left cross, and fix it the most stably as possible. Fix the center of the cross there for a few seconds, and then you fix the cross at the right. Again, you fix your gaze on it, and probably you will see something in this side. Is it working for someone? Yeah. Okay, so this is an after effect. So, and probably you see some square there. You see some square, and those square are not as the same color as the former square. And actually, it is opponent color perception. So it gives you the opponent of the red there, which is cyan, opponent of the green there, which is some magenta, let's say, and the yellow on the yellow there and the blue there, which are almost the same as the original. So what does this experiment says? It says that the visual system adapts to the stimulation. So when you fix your gaze there, actually you fix also the color on the retina, the red on this part, the green on this part. And then when you fix on the other cross, what you see is what the system has encoded to cancel those colors. So one of the principles of the vision is to remove what is known in the scene. So to improve the accuracy of the coding in the visual system will remove what you see actually. And when you fix there, the red square is being removed by the visual system, and then when you fix there, you will see what the visual system has encoded to remove the red. So it's something like a cyan. So this is to illustrate that color vision is a complex phenomenon, and especially it is adapted. It adapts to the environment. So what is a color? There is a long story of color actually, and one of the beginning of this story is, I would say, as the physical history of the physical history is the decomposition of the white light by Newton. So what he does actually, he projects a white light, a pencil of white light on a prism, and then he sees that the prism decomposes the light into several components, and those components correspond to colored light. So we can define a color as being a part of the spectrum like this, okay? So formally, we can say that color is ever a part of the wavelength spectrum. This part could be even monochromatic, could be very thin and be monochromatic, or a color could be a complete composition of those monochromatic lights. So it could be a continuous function, which is composed of several components. So the first mathematical property of color is the vector space. So this has been shown by Maxwell with this color mixing stuff. So it consists of several color plates like red, green, and blue, and those plates are putting on the same apparatus, and you can with this system change the area of each color on the system. And when you rotate this, it makes the different color. And what Maxwell observed at that time is with this kind of system with only 3 colors, he is able to produce any color sensation. So the yellow, the magenta, the orange, whatever color you imagine, you can produce it as a combination, a temporal combination of those 3 different colors. So it has been formalized, and finally, it has been shown that color vision is a vector space. So you can guess the color of a color composed by 2 other color, like the green and the red. If you mix the green and the red, it gives you a yellow, and this yellow is a vector composition of the green and the red. And this is the definition of a color as a vector space. But it's not a metrical space, because if you want a metrical space, you have that those 2 colors, the red and the green, be integrated into an orthogonal space, like this one, which is a reddish color there and a greenish color there. But to render a vector space into a metric space, you have to have this orthogonality principle somewhere. So this is an ancient question, and this is still a not solved question: is it possible to put the color space into a metrical space, and what are the orthogonal components of this? So this is still a living question. So now I will speak about the quantum and the wave nature of light. So light is also quantum in nature, because for different reasons. So we will see that color and light is a wave function, and this wave function should respect the conservation of energy for an isolated system. So it follows the law of conservation of energy. So if you look at the component of the wave, corresponding wave, it should respect the Schrödinger equation. So it should be a solution of the Schrödinger equation. So it should be something like a quantum things that respect the time evolution of the Schrödinger equation. In other terms, we can define actually a light or a color as a spectrum, and if this spectrum is along the nu, so the frequency of the wave, then the height of any point of the spectrum corresponds to a particular energy. For example, this part of the spectrum there corresponds to an energy which is kappa h nu, and h is the quantum, let's say the quantum part of the energy, and it corresponds to the Planck constant. So when you have a spectrum like this, if the spectrum is written in terms of nu, it means that this function actually represents the different level of energy for the different waves that compose the light. So it is a good input as a model for color vision, because it rely any point of this function with a quantum energy with a number of quanta. So this level there correspond of a number of quanta given by this wave. So the number of quanta is kappa. And with this description, we can use either a continuous spectrum or discrete spectrum like this, let's say yellow, this particular color. I put it in red and green, but it's yellow actually. It's around yellow. And this is a good description of light. But usually in color vision, we use the lambda variable instead of the nu. It's a historical reason, and it also, for some reason, we use this nanometer, so this wavelength instead of frequency. And in the model, we also use xi as a variable, which is between -1/2 and +1/2, and it represents the new variable into a different range. So don't be surprised to have these three different description of a light going together in the following of the talk. So actually, there is a long history on several experiments that try to measure what the visual system is responding to. So the question is, could we guess how the color vision works, and could we measure how human encode the information, the color information? So for that, there is two main different experiments that have been done. This one is the flicker photometry. So flicker photometry measures the overall sensibility of the eyes along the wavelength. So the experiments work as this one. So choose a monochromatic light like lambda there. I can also put the full screen mode. Yes. So get a monochromatic light at lambda and put it on a screen, and choose another monochromatic light, lambda plus delta lambda, and put it on the screen, but you alternate the two presentations. So you present lambda and lambda plus delta lambda, different light. Okay. And if you do that, and if the two lights are not perceived at the same intensity for the observer, then you will see a flicker, because it will be dark, bright, and this alternation of dark and bright will make a flicker, and you see a summer flicker. So you ask the observer to adjust one of the two lights in order to reduce the flicker. And the way you adjust this, the amount of adjustment will give you finally the relative intensity of the two lights. And this is the way people have measured this function close to close, point to point. So they compare 2 points close together, because those two lights, because they are close together, they are not differentiated in color. They are just differentiated in intensity, in the importance, in the intensity. So this results in this function, which is an average between 24 observers, and this function is called V lambda. But this function only talks about the intensity of light. It doesn't talk about the color perception of light. So there is a second experiment for that. It's called color matching. And this experiment works as follows. You choose three primaries, one in the red part of the spectrum, one in the green part of the spectrum, and one in the blue part of the spectrum. So those primaries are monochromatic also. And then you choose a test light, which is W there, and you ask so you project the W light in the screen, and you project the combination of R, G, and B on another part of the screen, and you ask the observer to adjust the perception of the two fields there, and by changing the amount of red, green, and blue, the observer is able to match those two lights. And then you get the RGB intensity the observer choose as a coordinate for this light. So those functions there represent the intensity of the red, green, and blue primaries in order to match any light. So for example, for W, you need this amount of the red primaries, this amount of the green, and almost no amount of the blue primaries. So I call those measurements like a quantum undulatory. Sorry, it's because they use monochromatic light. In some sense, those monochromatic light could be expressed also as a number of photons arriving the eye. So because they use monochromatic light, it is similar to guess what would be the quantum characteristic of those different primaries and function. Finally, those RGB function, color matching function, are being transformed into X, Y, Z, because there is negative value, and then all are positive there. And also Y correspond to V lambda, correspond to this V lambda measure there. So what we can do with those functions, so let's consider the XYZ now. So what we can do is to represent those functions as a in a three-dimensional space, so as a volume in a three-dimensional space. So how it works is you choose three axes, X, Y, and Z, that correspond to those functions, X, Y, and Z. And then you use lambda as a parameter. And when you go from 400 nanometer to 700 nanometer, it draw a line, this black line. So for example, if you start at 400 nanometer, you have Z growing first. So if you start there, Z growing first, and then this is Y that grow, and then this is X. So it draw this pattern there. And this is the representation of the monochromatic light into a three-dimensional space. And then CIE have proposed to project this three-dimensional space into a plane. And this plane is the magenta there. And any point of the black line project into this red contour there. Okay. And this is called the spectrum locus. So this is the locus of the spectra in the space of color vision. And those functions, because of the color matching experiment, those functions correspond to the human perception of color. Okay. But there is a problem with this model, because if now you look at the differences in between two colors in this space, in this two-dimensional chromaticity diagram, actually you found that the just noticeable difference in between two colors is not a uniform contour. It is an ellipse, so depending on the direction you go, the differences is perceived less or more. And from point to point in that space, the ellipses change in size and orientation. So it means that this space, even if it's measured on the human by the color matching experiment, this space is not a metrical space. So we cannot easily put a metric on that space. We developed some model of this non-linearity in the color space, and we found a function like this one, y equal x over x plus x0, where y is the electrical current in the retina neuron, let's say, and x is the input light, so is the input of the photoreceptor light, and x0 is the adaptation of the photoreceptor. And this function is adaptive, so depending of x0 it changes. This function could be for this x0, but it could be more sharpness for a smaller x0, or it could be more flat for larger x0. But with this function, we can model actually the ellipses as being a perfect uniform detection in the brain. But through this function, this perfect detection in the brain corresponds physically to an ellipsis. So this is the kind of model we have developed. Okay, so this is the history of color vision. So it's based on the measurement and the observer, but this space is not very accurate because we cannot design a clear metrical space. So now let's switch in a relativistic quantum color vision. So color vision is quantum. It's quantum for different reasons, but one of the most reasons is the visual system is sensitive to a single photon. So this is also a long history in this research. But the recent article by Tinsley et al. Show this is the apparatus they use, and they have a photon beamer there, and this photon beamer is sent through the eyes, but it also sent to a sensor, so they can know when the photon is getting out this system, so they can correlate the measurement of the photon by the sensor and by the eyes. And they show that there is a correlation, and this correlation show that the sensitivity of the eyes could be at a single photon. But for sure, this sensibility of a single photon is for dark adapted eyes, so for very dark adapted eyes. And in natural viewing, as seeing the screen, for example, there is a million of photons arriving, and probably the eyes is not able to distinguish between million and million plus one, okay? So this is a particular experiment, but at least it showed that the visual system is able to adapt so nicely that a single photon could be detected in some cases. Okay, from a mathematical point of view, we can say also that the space of metamerism, so the space which relates which color are the same, actually, is a subspace of a Hilbert space. And this part is very very similar to what we know in quantum physics. So we know that we can create having the degree of variability of the quantum system, we can build a subspace of the space of every system, if you want, and this corresponds to what is done in color vision, because a subspace could produce the metamerism space from an infinite Hilbert space. I will come back later on that. Also, color vision is relativistic. Why it is relativistic? It's because if you look at the appearance of a color, actually it's well described as a cone in the hue, chroma, and value space. So this is this cone. So you have the hue there, okay, the chroma or the saturation, I will call it saturation in the following, and the value there, which are from the black to the white. The hue are the different hue on the cycle, and the chroma is the departure from the white, from the gray axis. Okay, is the chroma, and the value is the intensity, so it's come from black to white. And this cone of hue, chroma, and value actually is very similar to the cone of light as described in space-time relativity, in special relativity. So Yilmaz showed this analogy in between the perceived color cone and the space-time cone. And also Yilmaz showed that the transformation between the transformation induced by change in illumination of the scene is given by a Lorentz transformation. So this is the same kind of transformation that you have in space-time relativity. Okay, this is the background. And now we will see how it works for color vision. So again, we get with this function there, and this function, which is the light spectra, which is the spectra of light, okay? So this function, we can associate a vector, f. So this is a vector associated to the function. And this is associated with a basis. So you could describe this function there as being the sum of a lot of any Dirac function you want. So, okay. And this Dirac function gives the intensity of the spectra of this wavelength or of this frequency. And then you can consider the space of light as being the space of all possible function of the frequency nu or of xi, the variable we get. Okay, So it's mean that you could describe any function as being a sum of the Dirac function. And this is the same in mechanics. This is very similar to what happened in quantum mechanics. And more formally, you can design a vector space saying two vectors corresponding to two lights, so F and G corresponding to two lights. So you can do the composition of this light and the multiplication by intensity, and then it is still a vector in this space. It is usual to design a scalar product in this space, and this scalar product is the integral of the two functions over xi. And you can also design a norm, which is the square root of the scalar product of the function with itself. And then we have the property of Dirac function, saying that the scalar product with a function in the function and the Dirac give you the value of the function at the Dirac position. So this is very similar to what we develop in geometrical quantum mechanics. So now how the metamerism space is constructed from this formalism. So actually, metamerism space is the space that say which spectrum are equivalent, so are perceptually equivalent. So we follow Yilmaz. We choose three functions actually: phi1 there, phi2 there, and phi3. And he says that those three functions are representative of an idealistic color space. It's not the real color space as measured by the experiment I show you, but it's a kind of idealistic color space. So let's follow Yilmaz with that. So let's now consider a function like d55, which is the natural daylight illuminant. And if you represent this function d55 by the free function psi1, psi2, and psi3, it will give you this red function. So this is the approximation of daylight function by the visual system. And actually, we are able to design an operator R, which do that work. So if you compute R of L, it gives you F. So this is simply like this. So F is a function which is a combination of psi1, psi2, and psi3. And then F1 corresponds to psi1 scalar F. And then you could write this projector R multiplying F. So it's mean that actually any function like d55 is represented in the visual system as a smooth function, this smooth function. And then the differences between the smooth function and the original function is given by this Q function there. And this Q function is oscillating in between positive and negative value. What is possible now is, because there is three functions, psi1, psi2, and psi3, that represent the color vision stuff, it's possible to put those functions into a three-dimensional space. So for that, we design psi1, psi2, and psi3 as the orthogonal basis of the color space, okay? And we design this projection operator, OE, which represents the eye, if you want. And with this projection, so this projection is defined easily like this, and says, again, is a kind of quantum things. And then if we project L by this OE operator, we get this L point, we get this point there. So to a function correspond a point. But now, because this function F is the projection, is the approximation of L by the visual system, actually, because they are metamer, they are representing in the same point in this space. And the difference in between those two functions, Q, is represented as 0, because Q is not visible by this visual system psi1, psi2, psi3. So Q is invisible for psi1, psi2, psi3. Okay, so now let's consider this projection again. So now if you get a Dirac function, like you project this Dirac function with O, it will give you a vector there. And if you move this Dirac function along the spectrum, along the Xi value there, then you can show that the vector will move along this envelope of the cone. Okay, so if you move this Dirac there, it moves along the envelope of the cone. And then it's mean that because light function are positive function of spectra, so it is a positive combination of Dirac, and because it's a positive combination of the Dirac, any light will project inside the volume of the cone. And so any light is inside the cone. So we can suppose that the visual system do not develop a representation for vector which is outside the cone, because visual system develop, okay, he learned the environment, and he has no reason to learn outside the cone. So we suppose the visual system is able to encode only light that are represent inside the volume of the cone. So now there is a second projection in the visual system, and this projection is along the unit hyperboloid. So any point inside the cone could be represented as a hyperboloid. So suppose this point, for example, you can have an hyperboloid that going to this point, okay? But we suppose that the visual system use only one hyperboloid to represent the world. At an instant of time, it use only one hyperboloid. So for example, this f function will be projected on the unit hyperboloid, and it resumes to f. So the visual system only represents color inside the hyperboloid, and we can call this little f color as a pure color. It corresponds to a pure color where f is any color. And then we have the metamerism property, so f equal g there, and this f is represented by the little f. I'm running out of time, but as everybody else does it, I can continue a few minutes. It's not long. I have four more slides. Okay, so actually, this cone have been described by Yilmaz as being the cone of maximal saturation. So the envelope of the cone there correspond to a saturation big sigma, which is the maximal saturation, and any light like this light f is encoded by a particular saturation. And what you can do in this cone, and it is the property of the cone, is that if you do a Lorentz transform, so if you do a transformation which is hyperbolic rotation, then the metric of the cone is conserved. So if you have a metric of the cone, which is this one there, so if you apply this transformation omega, you conserve the property of the quadratic form and the metric. And this is what Yilmaz described as being adaptation to a new illuminant. And this is the diagram there. So suppose you are adapted to this illuminant, X3. So you can design this hyperbolic model, the cone and the hyperbolic model. So now suppose the light change, so the illuminant change, and then it will be represented by the Y3 there. Then there is a rotation, there is a change in the metrical space, so there is a change in the hyperbolic space. And what Yilmaz says is that the white point, which is defined there, then in the new illuminant, this white point will be defined by W prime there, W prime there. And this W prime is actually sliding along the hyperboloid, along the red hyperboloid. So when you change illuminant, you change it in a way that the white point, slide along the unit hyperboloid. And this is given by this Lorentz transformation. Okay, so Yilmaz have shown an experiment to demonstrate this property. So the experiment is called the two rooms experiment, and is made as this one. So it's not a real experiment because I never see some result on this. So it's just a descriptive experiment, if you want. So if you have a light source like I1 there in one room, and you have another light source in the other room like this, And the two rooms there is a hole in the two rooms, and this observer is adapted to this illuminant, but he could see the white paper, a white paper there, which is illuminated by this second illuminant. And there is a white paper there, and the observer could see the white paper there and illuminated by this illuminant. And we suppose that the observer is adapted to the illuminant in the room in which he is. So when the observer looks at this paper, it is white because it is adapted to this illuminant, and this illuminant reflects on the paper. But when you look to the hole, you see there's white paper a bit saturated, so a bit colored, and this because this paper is illuminated by this illuminant. So there is a sigma difference, so there is a saturation difference in between the two papers. And now if the observer go to this room, he will see a shift in saturation too, but minus sigma. And then there is a second experiment when the second room is given as a very monochromatic red, and then the observer see this paper red, and this red is actually the maximum saturation sigma. And the third experiment is you have the yellow illuminating the second room, and in the first room, the illumination goes from D55 to D50, so there is a change in illumination there. And then the observer expects a shift in U, okay? Alors, I don't want to enter into detail, but Yilmaz does a model of this, and this model shows actually that the transformation is really a Lorentz transformation. So we confirm experimentally that this transformation following a change in adaptation, so there is a change in adaptation, and this change in adaptation will behave like a Lorentz transform. So with the model I have present, we can see D55 and D50 as being two illuminants, and then they are represented by those three functions, C1, C2, and C3, and we can represent this like that. And so the D55 is this illuminant, D50 is this illuminant, and we can suppose that the two hyperbolic models are rotated by the change in illuminant. And what is important to say also here is that we can see that from a different point of view. So it's kind of different point of view. So when you change the illuminant, it's like the visual system change of the point of view. But it's not a point of view on space, it's a point of view on color. So this explicitly show that there is also in the visual system a point of view on color, and not only just on space because you move your head or you move your gaze. So there is the same kind of processing in the color system. Okay, so in the lab we do an experiment, and this experiment is the following. Actually, we show to the observer this stimuli. So probably you see it going to the right now, and with a few times it goes to the left like that. Okay, it's called the minimum motion. It's called the minimum motion stimulus. So it goes to the right and go to the left. And why it goes to the right and why it goes to the left? It goes to the right or the left because the perceived intensity of the red and the green that compose the stimuli is modulated. So if the red is more intense than the green, it goes to right. If the green is more intense than red, it goes to left. And we use this stimuli to actually guess the direction of the luminance vector in the color space of a computer. So this is the color space of the computer we have calibrated, okay? So you have the red, the green, and the blue of the computer, and this is embedded into an orthogonal space, A, B, C. And then you have here a point, so it is a color, and around this point, we measure the direction of the luminance vector. And when we integrate this vector field, so for several points we have a vector, so it is a vector field. And when we integrate this vector field, it gives us this hyperbolic model. And this is actually representing the observer looking at the screen. So this is the cube of the screen, and this is the hyperbolic model corresponding to the observer. For sure, we found that for different observers, the model changed a bit, but okay, we do not enter into detail. So this concludes my presentation, and now I just say a few words about relative quantum color vision and its relation with relativistic quantum mechanics. So color vision is not a quantum model for everything. For example, there is no polarization in color vision, so human vision is not sensitive to light polarization. There is also no spin for photons, so probably color vision does not talk about the spin problem in quantum mechanics. And also, there is differences between color space and space-time. So see, this is just an analogy and is not there. For example, there is no time dilatation nor length contraction in color, but there is in space-time. It also, we can say that the coordinate is not the same, and the variable are not the same because there is no velocity. In space-time, we talk about velocity acceleration, and in color vision, we talk about saturation and brightness and hue. So there are different variables. But the analogy exists, and there is some relationship between color vision and fundamental physics. For example, there is no measurement problem in color vision. There is no stimuli that you cannot say in some sense if it's green or blue or red. So there is a reduction of the wave packet if you want, but this reduction is deterministic, and this gives us the sensation of color as we expect to have. And there is no probability in color vision. You cannot say, I see this color probably right or probably green. There is no probability. The wave packet reduction is always the same, and always it works. I mean, there is no ambiguity on that. So I think maybe color vision could be a way to describe quantum mechanics in a non-probabilistic term. But in what I show also, color vision is not a simple measurement system. Actually, because of adaptation, it's like the color system take a point of view on the color of the scene, and this point of view is like a different measurement system. It's like the eyes has different measurement system, and depending of the overall environment of the scene, the measurement change. So the metric of the color space change and the measurement changes. Okay, and there is also interaction between system and observer in color vision, because we know that there is differences in color vision among observer, and also we know that the particular physiology of the observer will determine this color vision stuff. For example, daltonism is physiological differences between observer, and it really makes differences in perception. And finally, what is very interesting is the perfect uncheck between quantum part and relativistic part in color vision. As I show you, quantum part give us a projection on the metameric space, and this projection actually directly shape the relativistic part, which is the hyperboloid inside this space. So this uncheck, I'm very confident that this uncheck between the quantum and relativistic part could be very useful for quantum gravity, because we can see also adaptation as a general relativity, because depending of the context, again, depending of the vector field around, you have a different space of color perception. That's it. Thank you very much.